Hello and welcome to Otten Math. In this edition of Otten Math, we are going to solve two problems that involve the triangle application theorems that we discussed in the prior lesson. So let's get with it. All right, number 19. We're going to prove that the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices. All right, so let's draw the diagram first and let's talk about how we're going to complete this proof. So we're going to prove the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices. Well, I can say that BD is congruent to DC by definition, right? I've just said that the midpoint of the hypotenuse. So BD is congruent to DC. So we need to find out if AD is congruent to BD and DC. So this is how we prove this particular, or solve this particular problem. I think I just labeled this as D, but now I've relabeled it as E. So what I'm going to do is I'm going to extend AE through to D so that AE is congruent with ED. So I have AE congruent with ED. So now I have BE and EC congruent. I extend my line or my segment AE through to D so that AE is now congruent with ED. And I've drawn these two tick marks here. So now I can say that AD bisects BC, and BD bisects AD. So ABDC is a parallelogram. If I have a quadrilateral that has two diagonals which bisect each other, then it's a parallelogram. Right? I'm going to say that angle A or BAC is a right angle by definition. We're told that the midpoint of the hypotenuse of a right triangle and BAC is a right triangle. So angle A is a right angle. So ABDC is a rectangle, right? And remember, the definition of a rectangle is a parallelogram with at least one right angle. In a rectangle, we know that diagonals are congruent. So now I can say AD is congruent with BC. Well, if AD is congruent with BC, then I know that if two segments are congruent, they're like divisions are congruent. And now I can say that BE, EC, and AE are all congruent. All right, let's move on to the second and last problem. I'm going to prove that if the midpoints of a quadrilateral are joined in order, the figure formed is a parallelogram. All right, so let's create our diagram. So I have a quadrilateral, and I'm joining the midpoints all in order, and I'm not saying anything about the quadrilateral other than it has four sides. In this case, it looks like I have a scalene quadrilateral, which means that all the sides are not the same length. And we want to prove that the figure formed is a parallelogram. Well, remember, if I have opposite sides that are congruent, both pairs of opposite sides of a quadrilateral that are congruent, then I have a parallelogram. So in the lesson, we learned about the midline theorem, which said that that the segment joining the midpoints of the legs of a triangle are going to be half the distance or half the length of the base of that triangle. So in this case, I have two bases. The first one we're going to start out with is going to be GC. All right. So if GC is the base and HB connects the midpoints of that parallelogram, then I can say that HB and FD are each half of GC. So HB and FD are congruent. In the same fashion, if I say that AE is now a diagonal here, and HF connects the two midpoints of the triangle with AE as a base, and BD connects the two midpoints with AE as a base, then I can say also that HF is going to be congruent with BD, and I apologize for the colors. I'm just trying to give you a visual example, but I know the colors are getting mixed up, so I will say that I'll mark this with 4 lines here, BD, and 4 lines here, 1, 2, 3, 4, with HF. So HF and BD are congruent, and I'll have 2 circles here for HB and 2 circles here for FD. So now I can say that it's going to be HBDF. So I have to correct this. It's going to be HBDF. The figure formed by joining the midpoints is a parallelogram because opposite sides, both pairs of opposite sides, are going to be congruent.